All right, guys, this is our last lesson for Unit 1. Our next thing we'll do is our study guide and test for this particular chapter. We'll move on to a new unit. So this chapter is just kind of taking some extra topics that have to do with linear equations and kind of putting them together. So just kind of a hodgepodge of things really going on here. So the first two topics are kind of related. Basically, finding equations of parallel and perpendicular lines. And then also, the last two topics go together. It has to do with these things called the lines of best fit, which we'll talk about as well. So they're separate ideas. They're not really related, other than the fact that they both have to do with linear functions. So I'm just kind of putting together, squeezing in a few similar topics here for our final lesson. So let's talk about parallel and perpendicular lines. Many of you guys have probably already had geometry. So what are these? So just a refresher. Parallel lines are two lines that do not intersect, and they have the same slope. Perpendicular lines are two lines that cross. So in the picture on the right there, you can see we have two pink lines that are intersecting each other. So they do cross, but when they cross, they make a 90-degree angle. So that's what it means to be perpendicular. But here's the really interesting part about these. Their slopes are negative reciprocals. So what that means is that if the slope of one of those lines was m over n, the slope of the other one would be negative n over m. So it's the reverse of the fraction flipped over, and also the opposite sign. And so those slopes will have negative reciprocal slopes. So for instance, looking at this problem here, one line has a slope of 2, the other one has a slope of negative 1/2. That's because this is 2 over 1, so if you flip that over and change the sign, you get negative 1/2, and notice that those two lines have made a 90-degree angle. So parallel lines have the same slope, whereas perpendicular lines have negative reciprocal slopes. So that is what we need to know about parallel and perpendicular lines. So let's go ahead and do example 1 here. So find the equation of the line that contains the point 6, 2 that is also parallel to the line given above. So they've given me a line, and they want me to find the equation of another line that goes through this point, and that line also needs to be parallel to the first line. Okay. Now, you do not have to draw a picture for this, but I'm going to draw a picture just so you guys understand what we're doing. So I'm going to start by graphing the equation they gave us. It's got a y-intercept of 2 and a slope of negative 3/4. And so that would look something like this. Okay? Now the point 6, 2 would be right about here. So that's the point 6, 2. Now can you guys imagine a line that goes through that green dot that's also parallel to the purple line? It would look like this, right? It's parallel to the purple line, and it goes through the green dot. So we already know what the equation of the purple line is. The equation of the purple line is right here. It's negative 3/4 x plus 2. The question is what is the equation of this line? In other words, we need to find the slope of this line and also the y-intercept. Well, this is going to be a lot like our lesson from last Friday where we found the equation of a line. It's a 3-step process. The first thing you need to do is you need to find your slope. Then you need to find your b. After that, you can write your equation. Now, how can we find the slope of that red line? Well, we know something very important about that red line. That red line is supposed to be parallel to the purple line. And why is that important? Because parallel lines have the same slope as each other. And we already know what the slope of the purple line is. The slope of the purple line is negative 3/4. So I'm just going to use that one. So my red line has to have the same slope as the purple line, which we know to be negative 3/4. So that's the main trick. After that, everything else is exactly the same to find the equation of that red line. So how do you find the b again? Well, what you do is you're going to use that formula, y equals mx plus b. You're going to plug in the y value that they gave you, which is 2 in this case. You're going to plug in the slope, which we just figured out. And you're going to plug in the x value that they gave you. Now, why am I using the 0.62? Because that point has to be on the line that I'm trying to find the equation of. I'm trying to find the equation of the red line. I only know of one point that's on that line, and it's the green one up here, the 6,2. So I have to use that x and y value to find the equation of the red line, because that's the only point on the red line that I know of. All right, so from here, we're going to go ahead and solve it. All right? Now, at this point, I need a little writing space here. We have a fraction to deal with. It happens. So we talked about this. You're going to put that over 1. You're going to multiply straight across. Negative 3 multiplied with 6 gives you negative 18. And 4 multiplied with 1. I put arrows here, otherwise it looks like minus. 4 times 1 is 4. We could reduce that fraction. Now, we talked about how to deal with this situation as well briefly. What if we have a fraction now? Now what do we do? Well, there's a few ways you can handle it, but the way that I do it is I multiply the fraction by the bottom number. So I'm going to multiply the top by the bottom. The reason I do that is because now they'll cancel each other out. And you're allowed to do that so long as you also multiply everything else by that bottom number. Okay? So what that leaves me with then is 4 equals negative 9 plus 2b. And now I have an equation that's a little bit easier to solve. I'm running out of space here, so 4 equals negative 9 plus 2b. All right, so add the 9, divide by 2, and we get a really weird b value, 13/2. Okay? So now we're ready to write our equation, and we're done. So the equation of the red line would have a slope of negative 3/4, because it's parallel to the purple line, which has a slope of 3/4. And we just calculated the y-intercept is 13/2. Okay, so that's how you can find the equation of a parallel line. I know that finding b was a pain in the butt, but that's all old news, actually. We've done all that. The new part was knowing how to find the slope of that red line. Okay, so let's go ahead and have you guys try that really quick. I'm not going to do 2 yet. I'm going to let you guys try one here. I guess I need to make up an example. I thought I had one, but I'll throw one up here real quick. Okay, so find the equation of a line parallel to y equals 1/2 x minus 5 that contains the point I guess 4 would be good. So find the equation of a line that's parallel to y equals 1/2 x minus 5 that contains the point 3/4. You do not have to graph this like I did. You can just do the math part that I did underneath the actual problem. But you can graph it if you want to. Pause the video here, and when you're done, you'll see the solution. Okay, So there's your answer there. Y equals 1/2 x plus 5/2. Back to our regular lesson there. Okay, so this time we're going to do something very similar to the last one that I did, but this time it's going to be perpendicular instead. Okay, so sorry, my board is having, it's an electronic board and it's having some lag time, so it's going to slow down my lesson a little bit. But anyway, here we go. So once again, I'm going to graph it, but you do not have to do that, okay? So I'm going to graph the original equation again. And this time it says, find the equation of the line that contains the point 6,2. So we're doing the same point again as last time. That is also perpendicular to the line given above. So this time, I want to find the equation of a line that does this. It goes through that point 6,2. But it makes a 90-degree angle with the other line. Okay? All right, so how do we do that? Well, we learned something about slopes of perpendicular lines. We know that the slope of this black line up here is -3/4. And what we learned about the slopes of perpendicular lines at the beginning of class today was that the slope of a perpendicular line is the negative reciprocal of the line it's perpendicular to. So if I take that -3/4 and I flip it over and change the sign from a negative into a positive, that is what the slope of the red line will be. It will be the negative reciprocal slope of the black line. After that, there really is nothing new. The rest of the problem is the same. So we're going to plug in our y value. We're going to plug in our slope. We're going to plug in our x. I think I plugged those in. Wrong number there. I think that's supposed to be a 6, actually. And then we solve for b. So multiplying straight across, we end up with 24/3. And 24/3 reduces nicely into 6. So we don't have to deal with fractions this time. And we get -4. So the equation of that red line up there then will be y equals 4/3, the negative reciprocal of the black line, x minus 4. So it's almost identical to the last problem. The only difference is that the slope is not the same. It's the negative reciprocal of this given slope. And once again, I'm going to let you guys try one of these. So same question on the last slide here that you guys worked on. I want you guys to solve this same problem again. But this time I want you guys to find the equation of the line that's perpendicular. And by the way, the symbol for perpendicular, if you can use the symbol instead to save writing, the symbol for perpendicular looks like that. There's also a symbol for parallel. I'll put that on the side over here. It's just like a slanted 11. But there you go. So go ahead and pause the video here, and when you're done, you'll see the steps and the solution. Okay, so there is your solution. The main thing I want to make sure you guys got down pretty well there is your slope. Notice that it's -2. That's because this slope is a half. If you flip that over, you get 2/1, which is just 2. And you change the sign to a negative, so it's -2. All right? So there is that. That's how you find the equations of lines that are parallel or perpendicular to a given line. All right. Moving on to a new topic here. So that's the end of parallel and perpendicular lines. We'll talk about our second big topic of the day, which is what we call linear regression, which is also a concept known as the line of best fit. So linear regression is a process of finding a linear function or a straight line that best fits the data on a scatter plot. Now the reason we have that is because in real life, things really just aren't all that simple. You know, in an equation in math class, we can make these lines because there's just these two variables that work together and they create a nice straight line. But in real life, there's a lot of variables affecting how things will turn out. And so even though there may be two variables that work really close together and it makes something look kind of like a straight line, there's other factors that come into play that mess it up and make it kind of wiggle and look like a mess. So on this little chart over here, you see that we can see that those dots are kind of going in a certain direction, but they are kind of scattered. So they're also known, this is also known as a scatter plot. So what we do in mathematics to model these sorts of scenarios in real life is we find a line that fits the data best. We want to find a line that is closest to all of the points. Okay, and that's pretty much it. So that's what we mean by a line of best fit. Now there actually is a correct answer, but we're not going to learn that today. Today we're going to do what's a good answer. Okay. I wanted to do a lesson where I could show you guys on a calculator how you can actually get the line that really is the best fit for the data. But once again, we're not in school. We don't have the graphing calculator, so I can't show you. And honestly, it was just an extra fun little lesson anyway for me, and it's not actually something you need to know for calculus anyway, so not a big deal. But there it is. So today we're going to learn how to find the equations of a line of best fit. And since we're really just estimating, it's not that there's really a correct answer per se that I'm looking for, but you can definitely be wrong if your estimate is way off. So just be aware of that. Now, before we go any further, since we're finding a line of best fit, sometimes a line of best fit will work really well, or sometimes it won't. So before I talk about this slide, let me go to this slide. In this case, on the far left top corner here, look at these dots. Look how closely they are together, and look how they basically make a straight line. That's what we would call a very strong relationship. Okay? Now we could see that there is a trend here. We can see like the dots are kind of scattered, but they are kind of going in a downward fashion, right? This one, you could barely see anything at all here, in my opinion. It's almost not even seeable, but if I had to say it was doing anything, it still kind of has like a downward direction to it. Now, at this point here, let's look in the far right. This looks like a really strong relationship as well. So let me relabel this. So strong over here as well. But they're going in opposite directions, right? This one's going down as we go left to right, and this one's going up. The one on the left is a strong relationship with a negative slope, and the one on the right is a strong relationship with a positive slope. And so we would say that it has a strong and negative or a strong and positive relationship. This is a pretty good relationship too. We can still see we'll call it a moderately positive relationship. Over here, this one that we did earlier, I would say this was like a moderately negative relationship. It's moderate because the data is not really as close to the line as the other ones. So it's not exactly a great fit, but it works. Same thing here. This is a pretty weak relationship. This is really weak. It still has a little bit of a downward trend, so we'll say it has a weak negative relationship, but it's very weak. You barely see it. This one, I could see a little bit of an upward trend in the data. So I would say this has a weak positive relationship. Okay? But when you come over here, this is, somebody could argue maybe this is a downward, I don't know. But basically, let me throw a few more dots on there just to make it completely unknowable. Okay. When you look at this, you can't really tell at all that there's any, you could never really draw a line there that's going to actually be closest to all the dots. They're so scattered around, there's really just no way to know. I lost my stuff. I want to bring back all the stuff I wrote. There we go. Okay, so when you have that kind of a situation, we would say there is no relationship. Now, what do I mean by relationship? I've been using that word a lot. What does that mean, no relationship? Well, in order to be in a relationship, right, you need two things happening, right? So, well, on all these graphs, there's a y and an x. And these graphs show how they're related. So for this graph over here, x and y have a very strong negative relationship. Over here, x and y have a very strong positive relationship. Over here, they have a moderately strong relationship, but it's negative. Over here, x and y have a moderately positive relationship. Over here, x and y have a weak and negative relationship. Over here, these have a weak and positive relationship. All right. So let me try to make some real life examples out of this. Like, let's say that you have a brother and a sister. Well, you have a very strong negative relationship with your brother. It means you hate him. If you have a moderately negative relationship with your brother, he kind of bugs you. If you have a weak negative relationship with your brother, he bugs you sometimes, but he's cute enough for you to live with him. If you have a strong and positive relationship with your brother, you're like best friends. If you have a moderate and positive relationship with your brother, you guys get along most of the time. If you have a weak but a positive relationship, well, so long as he stays in his room and you stay in your room, we can live together. It's not a big deal. Down here, you're not even going to live together anymore. You're not related. I'm done with you. Get out of here. There's no more relationship. So that's the idea there. Now, you guys will notice that there's some numbers on the screen here. Underneath of each box, there's a number. 1 is as strong as you can be. So 1 is the strongest negative relationship, and positive 1 is the strongest positive relationship. 0 means no relationship. So anything between -1 and 0 is going to be negative, but the closer it is to -1, the stronger of a relationship it'll be. The closer it is to 0, the weaker of a relationship it will be. Likewise, on this side, anything between 0 and +1 will be a positive relationship, but the closer those numbers are to 0, the weaker of a relationship it is. The closer they are to 1, the stronger of a relationship it is. And the strongest relationship you can get is if the dots all lie on the same exact line. So, in real life, sometimes variables are very strongly related to each other, and you can really get some very good predictions from the data because they're so strongly related. Other times, it's not so much the same. Like, for instance, like in, let me try to think of something. Like, if we're talking about gas mileage of your car, the number of miles, or the amount of gas you use is very strongly related to how many miles you've driven. Okay, very strongly related. It's almost like you can predict, right? You can predict, well, if I've driven 50 miles, you can actually predict how much gas will be left in your tank, and you'll probably be very close to being right. That would be a strong relationship. But like, let's take a look at like in the world of psychology. I heard a study once where they said that the hotter it is outside, the more likely it is that somebody will get into a violent altercation, a fight. For some reason, heat makes people angry. That's not always true, though, is it? Some people, it doesn't matter how hot they get. They're just pretty laid-back people. They're not going to get angry just because it's hot out, right? My guess is that data would look like this. Yeah, in general, you would see that there's a relationship between heat and anger and fights. but it's a very weak relationship. It's not always going to happen. Can't really predict it that well. So that's what we mean by relationships and positive versus negative. So let's go back a little bit here. What is a correlation coefficient? Well, a correlation coefficient is the number that was under each one of those graphs that I showed you on the last page there. It's a number that's between -1 and 1, and it tells you two things. It tells you the strength. In other words, the closer it is to 1, the stronger it is, and the closer it is to 0, the weaker it is. But it also tells you the direction. If it's negative, it goes down left to right. If it's positive, it goes up left to right. So it's a number between -1 and 1 that tells you the strength and direction. Okay? So not all lines of best fit always have to be straight lines. For instance, what if you saw data that looked like all those little circles up there? Well, you could do your best to draw a line of best fit with a straight line. I would say I would just ignore these ones because they just kind of seem to get in the way, and I would just draw a straight line here, right? But that would be a linear line of best fit. Later on in the year, though, we're going to learn about these things called logarithmic equations. And logarithmic functions actually look like this. And so guess what? A logarithmic function would be a better way to try to fit the data. And that's what we would call a nonlinear regression. In other words, you can have lines of best fit that aren't straight lines. You could find other ways to connect the data. And we won't be doing any of that this year. Something maybe you'd get into if you took statistics next year maybe. It's mainly something you do on a calculator. But just giving you guys some perspective there. All right, so anyway, so that's the background. That's what linear regression is, lines of best fit, correlation coefficients, all that good stuff. So what am I going to be asking you guys to do? I'm going to ask you guys, I'm going to give you some data, and I'm going to ask you to estimate the equation of the line of best fit. Okay? After that, I'm going to ask you to classify that relation in two ways. I want you to tell me, is it a positive or negative relationship? And then I want you to tell me, is it a strong or a weak relationship? So, we have two parts. Find the equation of a line, and then determine what the relationship's like. Strong or weak, and positive or negative. All right, so let's begin. Now, notice there's a key word there. It's estimate. Even though there actually is an answer to this question that's exact, we're going to estimate. To get the exact answer, either A, you have to do a lot of math, which we're not going to do, and it's not necessary, or we could just use a graphing calculator, which we can't do. So we're just going to estimate and get close. So what you would want to do is, if I were you, I would try to pause the video here and you guys see if you can draw a line of best fit. Where do you think that line would go that would best fit that data? I'm going to draw my answer now. If I were drawing a line of best fit, I would have it be like right about there, right? I feel like that's the line that's closest to all of the points. Okay? So, the first thing you want to do to find your line of best fit is you want to sketch it first. After you do that, you're going to pick 2 points on that line. So I said pick 2 points that are on the line. In this case, I'm going to go with this one, and I'll go with this one right here. Now, it's possible that where you chose to draw your line, even though that's the best line, maybe it doesn't actually touch any of the points. In that case, just pick any 2 points that are closest to that line. Okay? So, at this point, we're ready to find the equation of the line. You just need to remember what we learned back in lesson 1.3. So this point looks like it has coordinates 165, 165. this one seems to have the coordinates of, it looks like it's a little bit before 180. I would say like 75. I would say like maybe like 175. And maybe like 170 for the height. Now, once again, we're estimating. So let's say you put 179 instead of 175. Are you wrong? No, you're not. We're estimating, so no big deal. Okay, but you're just going to pick out the numbers that are close. Now, you would be wrong if you said 200. It's definitely not 200. But if you're only off by a little bit, you know, obviously that's okay. So, how do we find the equation of a line now? So, step 1, sketch the line of best fit. Step 2, pick 2 points that are on or close to that line. Step 3, find the equation using our old method that we're already very familiar with, the 3-step process. Find your slope, find your b, write your equation. So here we go. We have x1, y1, x2, y2. Now for this problem, we don't have our slope already. We actually have to calculate it using our slope formula. So I'm going to do y2 minus y1 over x2 minus x1. And that leaves me with 5 over 10, which is 1/2. That worked out really nice, you guys. Now, if on your problem, because half is actually a pretty nice slope to have. I was kind of thinking that maybe I would have ended up with something really ugly like 5/13 or something. You may end up with an ugly slope. If you do, I don't mind if you just change it to a decimal and use a calculator for the rest of the problem. Or if you want, you can just leave it as a fraction. I got kind of lucky and just ended up with a nice fraction. But let's go ahead and continue here. So now part B. For part B, we pick one of these points. I'll just go with this one here. You're going to plug in a y value, your slope, and an x value. And then you can solve for B. All right. So half of 165, what would that be? 82.5, I think. Notice I'm not using fractions. When you get really weird numbers, I say just forget fractions altogether, just go straight to decimals. And then if I subtract 82.5 on both sides, I end up with 82.5 equals B. So there's my B. So I've got my M, I've got my B, and I'm ready to write the equation. The line of best fit then, my estimate would be 1/2 x plus 82.5. Now, since we're estimating, if I asked you to do this on your own, are you going to end up with the same answer with me? No, you wouldn't. All right. So I got interrupted with a question I had to answer, so I kind of forgot my train of thought of where I was, but I just came back. Anyway, so I got this answer. Like, I think of what I was saying is that you may not have gotten the same answer, but you should have been close. So for instance, suppose someone else had done this problem, and well, you see how I got half, right, which is about 0.5. But let's say that they got like 0.6 x, and their y-intercept was a little different too, like maybe it was 80. Well, that would be okay. I mean, that's close enough. You're pretty much getting it. But I mean, I shouldn't see something weird like y equals negative 3x plus 1. That would be way off and completely wrong. So when we're estimating, so long as you're close, you're good. And you may be wondering how close is good enough. Well, I don't have an answer for that. But unless it would be obviously wrong to everybody, if I graphed your line and it looks something like that, then it would be wrong. So it would have to be pretty bad for me to count it as wrong. So long as it's pretty close to what we had, you're in good shape. Now, we're not quite done yet, though. The question also asked us to talk about the relationship a little bit between the variables x and y. So how well does this line of best fit describe the relationship between x and y as we see in this scatter plot? Well, if we go back to that chart that I had you guys looking at earlier, look how close these dots are. Well, in my opinion, they're not quite this bad, but they're not this good. Well, actually, let me back up a little bit. I think it's a positive one. So let's look on this side. They're pretty close to this, I would say. They're definitely not this good. They're not this scattered. They're pretty close together. So I would say that it has a moderately strong positive relationship. Okay, so for part B, how would you classify the relationship? I would classify this as moderately strong, or I guess we don't need to say strong, we just say moderately. Moderate positive relationship. It's positive because the slope is positive. So I'd say it's a moderately positive relationship. So from here on out, I would say, let's just review first. Sketch what you believe to be the line of best fit. Pick 2 points that are on or closest to that line. Find the equation of the line using all the standard stuff that we're used to doing. And then tell me what that relationship is like. In other words, where would you put it on this chart? Let me go back a little bit. There we go. Where would you put it here? Now in your homework tonight, they're going to give you a bunch of graphs like this, and they're going to give you a bunch of R values, and you have to match the right R value to the graph. So my recommendation to you would be to just get out these notes and take a look and see what each one looks closest to, and use that as your guide. Okay. But anyway, here's one for you guys. I would like you guys to do this problem. Go ahead and pause the video here, and when you unpause it, you will see the solution. Okay, so once again, you probably did not get exactly what I got, but so long as you got something close. So here's my answer. As a decimal, it's 0.15. As a fraction, gosh, it'd be like close to about 3/20 or something like that. I think that's right. And then my y-intercept is about 2.5, or maybe a little bit more or less, depending on how you estimate it. But there it is. So long as your slope and y are pretty close, that you're good. And by the way, I just figured out that, I just remembered, I should say, that instead of calculating your y-intercept, you can actually just look up here and see. I mean, by calculating it, I got 2.45. But when I look up here, my y-intercept, where it touches the y-axis, it actually looks like it's probably more like 2.7. But once again, we're estimating, so it doesn't really matter. And how would I classify this relationship? It's positive, and I would say that it's another positive moderate relationship. It's not strong, but it's moderate, I would say. Okay? And so there's that. And I think that might do it for us today. So we're all done. Next time we'll be assigning you guys a little study guide to work on, and see if you guys have any questions about that. So, till next time.